Good morning, friends. Today we will see the formulation for quadrilateral isoparametric elements. So last time we have seen the definition for isoparametric. What do you mean by isoparametric elements? And how to find out the safe functions for isoparametric elements by using natural coordinate systems. So whenever we do the formulation based on isoparametric, we have to use the natural coordinate system. And also we have seen what is natural coordinate system. Now, and also we have derived the safe functions for 1D elements, and we have seen how to formulate the element stiffness matrix for 1D element. Now today, let's see the quadrilateral elements. So what do you mean by quadrilateral elements? The quadrilateral elements has always 4 sides, and since we are using natural coordinate system, so their values always vary from -1 to +1, and hence the whatever is the shape of the quadrilateral element, so mathematically the element is always a square element. Now let's see the various types or shapes of the quadrilateral elements. So the standard is a square element, then a rectangular quadrilateral element, trapezoidal quadrilateral element, then parallelogram element, or the element may have the curved boundaries. So in isoparametric element, whatever is the shape of the element, the center of the origin is always taken at the center of the element. And the natural coordinate system xi and eta is used. So for each element, so we have to consider xi and eta as the natural coordinate system. So for this, the coordinate system will be like this for trapezoidal element. Again, for this, the coordinate system we have to consider this way. And the element with curved boundaries, 4-sided element with curved boundaries. So this is xi coordinate, this is eta coordinate. So this is a square element, this is rectangular, this is trapezoidal, then parallelogram type, and this is element with curved boundaries. So each and every element, whatever is their shape, the element has 4 sides. So what are the properties of this? It has always 4 sides for quadrilateral elements, 4 sides. Then the coordinate system used is a natural coordinate system. Then mathematically, the element is a square element. Is a square element, irrespective of its shape. And sizes or values, size varies from -1 to +1. So it helps to fit any boundary conditions. Hence, any irregular boundary can be mapped easily. Can be mapped easily. So, and also we know that the finding out stiffness matrix by using natural coordinate system is very easy. Now, so we have to always assume in the beginning a displacement function. Now, how to assume the displacement function for quadrilateral element, that is u equal to n1 u1 plus n2 u2 plus n3 u3 plus n4 u4, because it is four-sided element, four-noded element. Then v equal to n1 v1 plus n2 v2 plus n3 v3 plus n4 v4. Then geometric function we have to assume. Geometric function. So again the geometric function is assumed or described by using the same set functions, that is x equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4. Similarly, y equal to n1 y1 plus n2 y2 plus n3 y3 plus n4 y4. And we know that we have used the same shape of functions to describe displacement and geometry function. Hence, such an element where same shape functions are used is called isoparametric elements. It means when same shape functions are used to describe both displacement and geometric functions. Displacement and geometric functions are called, then the element is called isoparametric element. Isoparametric element. That is the degree of shape function or interpolation function that is the degree of shape function or interpolation function is same for both displacement and geometric function. So this is about what is meant by the isoparametric element. Now, how to formulate the element stiffness matrix for quadrilateral element, that we have to see. Now next, let's consider formulation for four-noded quadrilateral element. Say four-noded quadrilateral element. Quadrilateral element. And the type of problem we are going to consider is plane stress analysis or plane stress or strain analysis. Since this is 4-noded element and degree of freedom will be 2 per node, that is U and V will be the degree of freedom. So let's consider 4-noded quadrilateral element. Whatever is the shape of the element, mathematically the element will be a square element. Say node 1, 2 and 3. So this is 1, coordinates -1, -1. This is 2, so coordinates will be -1, -1 and 3, 1, 1, 4, -1 and 1. And the origin is to be considered at the center. So this is xi coordinate and this is zeta coordinate. Now the displacement function assumed for this is displacement function at any point within element can be defined as u equal to n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. Just now we have seen this. And v equal to n1 v1 n2 v2 plus n3 v3 plus n4 v4. Now next step, we have to calculate the shape functions by using natural coordinate system. Now the shape functions, the n1 is given by using Lagrangian interpolation formula. So n1 will be in xi direction, this is xi minus xi2 divided by xi1 minus xi2. And in y direction, we have eta minus eta 4 divided by eta 1 minus eta 4. Now substitute the coordinates. Substituting coordinates. So xi minus xi2, so this is xi minus xi2 is 1, xi2 is 1 divided by xi1 is minus 1, again xi2 is minus 1 into eta minus eta 4 is 1 divided by eta 1 is minus 1 minus 1. So this becomes, so this is minus 2 will be 4, and again we can write down this in this form, 1 minus xi 1 minus eta divided by 4 will be the n1. Similarly, let's find out the next shape function n2. In xi direction we have, it is xi minus xi1 divided by xi2 minus xi1. In eta direction, eta minus eta 3 divided by eta 2 minus eta 3. So the shape function n2 is given by xi minus xi1 is minus minus plus 1 divided by xi2 is 1 again plus 1. So eta minus 1 divided by this minus 1 minus 1. So now this becomes, so 1 plus xi 1 minus eta, and this is 1 plus xi, just by rearranging 1 minus eta, so this one negative will come outside the bracket, and here this minus plus becomes plus, so this is 4. So 1 plus xi, 1 minus eta divided by 4. Now similarly, we can directly write down the remaining shape functions, n3 is equal to 1 plus xi, 1 plus eta divided by 4. Then n4 is equal to 1 minus xi, 1 plus eta again divided by 4. Now we have calculated the shape functions. So before we proceed further, we can check the properties of these shape functions. We know that the properties of shape functions, that each and every shape function will have unit value at its own node and 0 at all other nodes. Let's consider the n1 function. Let us consider n1 function. So n1 is equal to 1 minus xi, 1 minus eta divided by 4. When we substitute xi equal to minus 1 and eta equal to minus 1, so this n1, so at node 1, value of n1 will be 1, and n2, n3, n4 will be equal to 0. Now we can plot this. Similarly, at node 2, n2 is 1, and n1 equal to n3 equal to n4 equal to 0. Then at node 3, n3 is 1, and n1, n2, n4 equal to 0. And at node 4, n4 is equal to 1, and n1 equal to n2 equal to n3 equal to 0. Now all these functions we can plot graphically. So these functions, now n1 will be like this. So this is n1, has unit value at its own node and 0 at all other nodes. So this is n1. Similarly, you can plot n2. So n2, that is here it is 1. So this is 1. So this is n2 function. This we have already seen for shape functions in Cartesian coordinates. So this is in natural coordinate system. So similar type of shapes you will get here also. So this is 1. So this is n3. Then the last n4. So this is 1. This is n4. So now we have checked the properties of shape functions. So it has unit value at its own node and 0 at all other nodes. Also you can check that n1 plus n2 plus n3 is equal to n3 plus n4 must be equal to 1. Now next, we have to express the geometric functions in terms of same shape functions. Let's use the same shape functions to define the geometric functions. So in order to derive the element stiffness matrix, we have to find out strains and stresses. So strains and stresses. So that's why the geometric functions are required. Now geometric function. So x is equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4. then y is equal to n1y1 plus n2y2 plus n3y3 plus n4y4.